Yeah. So if you look at the Zumbomnim PR, then it tried to implement multiplication over quartic extension field, squaring and inversion. And before, I think at quadratic we use a Karasuba, maybe for cubic, maybe Karasuba, but for the first time yeah, I'm not sure about that. Yeah, anyway, this time quartic extension field try to use Jungkook multiplication. Then I thought that it's very good time to describe what is Karasuba and what is Jungkook. And I think for cubic inversion and for quartic inversion together, they use something called Frobenius mapping to compute inverse. So I think it's very good to know this first and then try to abstract the code later. That's why I prepare for this the presentation. So the context of the Karasuba multiplication is like something like this. So maybe we could use this inside the big precision multiplication too, but I try to limit the scope inside only the multiplication within a extension field. So extension field is typically written as like this form, f to the p to the k. Yeah, for simplicity, I use p, but it also works for binary field too. So technically, I shouldn't use p here. But yeah, for simplicity, let's think of it as a prime field. And let's say we write the extension field like that with a x coefficient, because if it's a quartic extension field, and then it will be like a3 times x to the 3, a2 x to the 2, a1 x plus a0. We can write the extension field as a as a polynomial form like that. And if you view multiplication as a high view, then it will be decomposed into two steps. One is polynomial multiplication. So we first multiply extension field together in a polynomial form, or extension field, and then we get the C prime, and we're going to reduction with the both by f of x. But in this case, intentionally, f of x, we typically use very simple form. For example, if it is a quadratic, then it will be something like this. If it is a quartic, something like this. We intentionally, we get the irreducible polynomial in a simple form. That's how the reduction was made very simple. You just replace x to 3 or x to the q or x to the 4 with a non-residue. We call this constant. We call this non-residue, -1 or xi or blah blah. So yeah, reduction is typically very simple in the context of the multiplication over extension field. So what we are care mostly is how do we simplify the polynomial multiplication. If you just do a normal approach, it will require you n square complexity. This n is like the number of the base field or number of coefficients. So the Karasuba algorithm is typical way to solve this problem with a divide and conquer in a two-way. I mean, if you split the problem into two, and then you reduce the size of the problem into half, and then you combine or something like that. This is big view of Karasuba algorithm. So for example, if you have a polynomial a and b or extension field a and b, first you're going to split it into two, a1 and a0, high part and lower part, and b1 and b0, high part of b and lower part of b. Then we can write the a with a a1 and a0 like that, and we can write b with a b1 and b0 like that. And then, as I mentioned earlier in the first step, we're going to multiply like that. This is a result of the multiplication. And the thing is, so we have then these three part, high part, which is a1, b1, low part, a0, b0, and 3, or mid part is A1, B0 plus A0 and B1. Sorry. So we're going to multiply these three parts. Using these three parts, so M1 corresponds to the high part, M2 corresponds to the lower part. The thing is like, how do we get this middle part using M1, M2, and M3? If you just do a normal approach, you need to multiply 4 times, and this one gets you just 3 multiplication. And so this will reduce the number of multiplication from 4 to 3. The thing is like, how do we get this middle part using M1, M2, and M3? And to do that, to compute A1, B0 plus A0, B1, we subtract M3 from M1 and M2. M3 minus M1 minus M2. Because it's a very simple form of multiplication, you are convinced that, this will get you this. Then the C prime X will be reconstruct like this, as I mentioned earlier. Then the last step is like final reduction. So but for something like this extension field, you typically just replace this one, x2 to the m to the just xi or beta or quadratic non-residue, then it's done. So if it is a quadratic extension field, the answer after the step 4 will be something like m1, m2 minus m1 plus m3 minus m1 and m2. This will be the answer of the multiplication.
When it's quadratic extension field?
Yes.
Doesn't it depend on m?
In this case, m is 1, but what do you mean by depending on m?
Is m the extension degree or?
Oh, extension degree over base field.
I see.
So for a base field f of p, for simplicity, I just treated base field as a prime field, but it can be extended to like part of extension field where the degree over base field is 2. So if you use this approach for like f4, f2 to 2, or f4 to the 2, you can use this to any quadratic field, extension field, and this will reduce the multiplication number O of k squared to O of k log 2, 3. And it will the recursively it reduced the degree of the polynomial from k minus 1 to k over 2 minus 1. And then the cost of the the cost of addition and subtraction will proportional to the number of your extension field, which is k, but the multiplication complexity will be reduced to 3 times t of k over 2. So the over time complexity is something like this.
I kind of remember like the polynomial multiplication can be done in n log n. I mean k log k in this case.
Yes. That is Tunku.
Oh, I see. Okay.
So you can do this using an FFT, right?
Yeah.
That's the way of the Tunku doing for multiplication. Tunku uses FFT kind of.
Okay.